Hey everyone, today we're going to be talking about Newton's universal law of gravitation, which deals with the forces in play when talking about how different bodies or different masses have an attractive force for each other, and that's going to be ultimately dependent on the mass. And oftentimes this topic deals with larger bodies, so we're going to be talking a lot about planets and how planets apply forces to other planets due to their size and their mass, and how gravity plays a role in that. So this is another one of Newton's laws called the universal law of gravitation, and it deals with how any two bodies can attract each other with a force that is going to be directly proportional. I will try and do the little fish here with the squiggly line, is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So basically saying that the attractive force between two bodies is going to increase the larger the bodies get, and it's going to decrease the farther an object gets away from the other. Now this attractive force between the two objects that is resulting from the mass of each of the objects is what we call the gravitational force. And it's represented by the equation on your reference table. F sub g is equal to big G times the mass of object 1, the mass of object 2 divided by the radius between the centers of those objects squared. So F of g is the force due to gravity, and we measure that in newtons, represented with a capital N, which is also a kilogram times a meter per second squared. M1 and M2 are going to be masses of the two objects that we're talking about and how they're going to be attracting to each other. And mass is always measured in kilograms. It's our standard unit, kg. R being the distance between the centers of the objects in meters. So that's going to be the distance between the centers of the objects. G is going to be a universal gravitational constant. This is given to you on the front of the reference table. It's equal to 6.67 times 10 to the minus 11th Newton times meter squared over a kilogram squared. And that's going to relate each of the other variables in our equation there. Now this law is only valid for spherical masses because they're going to be pretty much uniform shape, size, density. So we're only going to refer to this for spherical masses of uniform density and masses that are small compared to the distance separating them, and that referring to planets. So you can see how an example of this might play out. Let's determine the magnitude of the gravitational force of attraction between Earth and the Moon. So we have Earth here, and we have the Moon, not trying to scale, rotating around the Earth, and that's the Moon. Now we have some type of attraction between the Earth and the Moon, and each of these has a mass. The Moon being smaller and having a smaller mass, we'll call that M2, and Earth having a larger mass, we'll call that M1. There is going to be a force of attraction between each of these, not just the Moon on the Earth, but the Earth as well on the Moon. And we can determine that. But first, let's define a couple of things. Mass of the Earth, this is given to you on the front of your reference table and your physical constant table. The mass of the Earth is 5.98 times 10 to the 24th kilograms. What a number. Mass of the Moon, 7.35 times 10 to the 22nd kilograms. And the distance from the Earth to the Moon, from the center of the Earth to the center of the Moon, not surface to surface, is 3.84 times 10 to the 8th meters. Another piece of information here that we're going to need to know is our universal constant, which is 6.67 times 10 to the minus 11th newtons times meter squared over kilogram squared. Now, to determine the magnitude of the gravitational force, that's going to be our F sub g. Gravitational force is also called the force due to gravity, our F sub g, and that's equal to our big G times m1, m2. I'm writing that as mi. It should be m1, m1 times m2 over the distance between those two squared. So this comes out to 6.67 times 10 to the minus 11th. There's a whole lot of numbers in here. 5.98 times 10 to the 24th. I'm going to forego my units for now so I can make sure I can fit all this in here. Times 10 to the 22nd. And we'll put that all over the distance squared of 3.84 times 10 to the 8th meters. We'll bracket that and square that on the outside. This gives us a gravitational force of 1.99 times 10 to the 20th newtons. And that is our F sub g, or force due to gravity. So that's the attractive force between the Earth and the Moon being applied, depending on your reference point, from the Moon to the Earth, or from the Earth to the Moon. Now, to try and think about gravitational force here for a second, let's take a look at the Earth itself. And the Earth is going to have, let's think of this as different force vectors acting towards the center of Earth. And we could show some smaller ones here. And what this shows, we can add these together and get the total force for our gravitational field, or we can look at them individually. So if we look at these individually, let's consider a couple different points here. Let's consider point A out here, and let's consider point B closer to Earth. So I guess to start here, if we consider points A or B, let's call them test particle A, test particle B. So if we consider a region in space where A or B would experience some type of gravitational force, such as around Earth, we call that a gravitational field. That's anywhere where some type of particle that has a mass would move in the direction of the force. That would be an indicator of a gravitational field. And these never really get to zero. It might get infinitely small, but even a small particle at the edge of our solar system is going to have some type of force vector moving towards the other planets in the solar system, regardless of how far away it is. It might be very weak, but it's still going to be there. So at any point in the gravitational field strength, or G, which we've known as the acceleration due to gravity, equals the force per unit mass at that point. And it's represented by the equation Newton's second law. If we rearrange this, G equals F sub G over M, where F sub G is measured in newtons, our force due to gravity, mass measured in kilograms, and our G is measured in meters per second squared. We'll also see this as newtons per kilogram. So we can see both of those. So coming back to this drawing here, point A, we have a much shorter vector. So point A here, I'm going to draw this in a different color. We have a smaller gravitational field vector. And where B is, we have a much longer gravitational field vector. Again, adding these together, we can get our gravitational field strength. But looking at these vectors separately gives us an idea of the magnitude of the gravitational field strength at that point. So at point A, this is particle point A is going to experience a smaller gravitational force, whereas point B is going to experience a larger gravitational force. So the closer an object is towards the center of another object's mass, it's going to experience a larger gravitational force. And we see that by the larger vector that B is closest to here. A is farther away from Earth. It is near a smaller gravitational field vector, which is indicating that it is experiencing a smaller force at that point. And the farther away we go from Earth, the weaker the gravitational field strength will become, which again, lower force, lower acceleration, it's going to have a smaller effect on a particle, and it's going to move that particle slower towards Earth. Now, the gravitational field strength has the same direction as the gravitational force acting on the mass. So the force is acting in the same direction as the acceleration, which holds true. We've been talking a lot about that. So gravitational field strength, or G, depending how we refer to this, is represented, we know this number well, 9.81. But when talking about the field strength, we're going to write that as 9.81 newtons per kilogram. That's a 1. It looks almost like a slash. 9.81 newtons per kilogram. But the acceleration due to gravity, so again, just depending how we're referring to this, is also, if we're talking about acceleration, 9.81 meters per second squared. Now this is only going to be when we're near the Earth's surface. And G is going to be uniform. So we're going to assume that that value is not going to change as long as we are near Earth's surface. So weight, we know, and we've talked about, and you've learned this throughout your years of schooling, that your weight changes depending on which planet you're on. If you go to the moon, you weigh less. Now, let's try and understand why. So the gravitational force with which a planet attracts a mass, so it's a force attracting a mass. We're a mass, and we're on Earth, and gravity is attracting us towards the surface, and that's what our weight is. The force with which a planet attracts a mass. Now, if we remove the gravitational force, we can still have mass, but we would no longer have weight. That's why when we move away from Earth and the gravitational force decreases, we essentially can become weightless. Not massless, but weightless. So if M represents the mass of Earth, capital M, And little m is the mass of an object on Earth's surface, and r is the distance for the center of Earth. We can see from Newton's law, or Newton's universal law of gravitation, that the weight, or Fg, so Fg is going to be representing our weight, of an object on Earth's surface is directly proportional to the mass of that object, because all the other quantities in that equation are held constant. So if we look at that, m1, m2, or r2, g is a constant, m2 of the Earth would be constant, and the distance, as long as we're near Earth's surface, we're going to call it a constant. So weight is directly proportional to the mass, and everything else is constant. Makes for evaluating that a little bit easier. Weight is a vector quantity. It is a force and has direction, and it's directed toward the center of a planet. And like all other forces, we measure them in newtons. Mass, on the other hand, is a scalar quantity, which is measured in kilograms. So seeing that weight will be measured in newtons. It's going to be measured in newtons. That is going to be a force value, so that is going to be a vector quantity. So I want to make sure we include that, or include direction when dealing with weight. Now, if we take an object, call it a rocket ship, call it an astronaut, call it somebody jumping off the surface of the Earth, the weight of an object, that person, is going to decrease the farther away they move from the surface of the Earth. And that's due to the decreasing gravitational field strength. If you think back to our diagram there, our vectors are getting smaller the farther away we move from Earth. If we add them all up together, we can get our lines of our gravitational field, but those vectors are getting smaller the farther we move away from Earth. Now, the mass of an object is always going to be constant because it's independent of its location in any gravitational field, be it the moon, a different planet, or Earth. The mass, or how much matter your body contains, doesn't change depending on the force of gravity. Your weight will change because the gravitational field is going to change, but your mass will not change. Now, the weight of an object can be determined by using gravitational field strength equation. Fg equals mg. Now, if we think of a weight of a, let's call it a 100 kilogram person, it's a pretty big person, times the acceleration due to gravity, we get a weight that's equal to 9,810 newtons. Excuse me, it's 981 newtons. 981 newtons. That would be towards the surface of the Earth. So this would be on Earth because we have an acceleration of 9.81 meters per second. If we consider the weight on the moon, we would have the same mass, but the g is going to be smaller. Let's say we were to call it, let's call it half. So let's call it 4.9 meters per second squared, and this is just for example here. Our weight would then come out to be half of what it was. about 490 newtons, and that would be our weight on the moon. This has to do with the gravitational field strength being smaller on the moon due to the moon's decreased mass. Since the moon is a smaller mass, it exhibits a smaller gravitational field, and therefore is going to attract other masses with a smaller force. So your weight on the moon is going to be less than it would be on Earth due to that difference in gravitational field strength, and ultimately due to the difference in acceleration due to gravity. I will show you the elevator scale scenario on a later video. For now, I will leave you with Einstein's favorite limerick. There was an old lady called Wright who could travel much faster than light. She departed one day in a relative way and returned on the previous night. Have a great day, everyone.